Jnanam Paramam Dhyayam. Knowledge is supreme.
Welcome to today's lecture on advanced transition metal organometallic chemistry. This lecture we are going to talk about an interesting aspect of transition metal allyl and enyl complexes that we have been discussing about in the last few lectures. These allyl and enyl ligands are very interesting type of ligands in the subclasses of various ligands that exist for transition metal organometallic complexes. Their uniqueness arise primarily for their sigma donor as well as pi acceptor behavior. So, unlike the very simple alkyl or hydride donor, which is or methyl donor, methyl ligand, which are simple sigma donor ligand, or like olefins, these allyl and enyl ligands can have both sigma donor and pi acceptor properties. From that perspective, we have looked into, in the beginning of the course, looked into various kind of interactions that occurs between the molecular orbitals of transition metal as well as that of the allyl and enyl ligand, and tried to understand how the interaction of sigma donation and pi acceptor kind of interaction originated from the overlap of these molecular orbitals or atomic orbitals of transition metals and the enyl or allyl ligands. We have also looked in the last lecture about different methods that are available in preparing the transition metal allyl and enyl complexes. By and large, what we saw, there are various preparative methods that are available for preparing this transition metal allyl and enyl complexes. All of them can be classified into 2 or 3 main type of reactions where most of the different examples would belong to. However, apart from that, there are few unique methods and unique strategies which also lead to the formation of transition metal allyl and enyl complexes. So, in today's lecture, we are going to finish up on this topic of transition metal allyl and enyl complexes by looking into the reactivity or the kind of reactions these transition metal allyl and enyl complexes exhibit, and then we are going to move on to another interesting topic, which are transition metal sandwich complexes. Now, these sandwich complexes actually started with the origin of ferrocene and then gradually expanded on to various combinations and various type of sandwich complexes. We are going to explore those in details as a part of this lecture. So, to begin with, let me just look into some of the reactivity of transition metal allyl complexes. The particular example starts off reacting diolefin complex of iron, resulting in formation of this transition metal allyl complex of iron, and then exploring the reactivity of the same. So, the reaction goes as this diolefin complex of iron carbonyl reacting with HbF4 and carbon monoxide, giving this allyl complex of iron, which is cationic in nature. Now, in the context of our earlier methods that existed on preparation of this eta 3 bound allyl transition metal complex, this particular method thus is a electrophilic attack, electrophile being the proton on the diolefin complex of the iron, resulting in eta 3 bound allyl iron complex in presence of donor ligands like CO, and the vacant space that is created as a result of the protonation and as a result of conversion of eta 4 bound diolefin to a eta 3 bound allyl is occupied by this carbon monoxide, and thus the iron goes from becoming FeCO3 to FeCO4. Overall, this is also 18 electron complex. This is 4 CO, that means 8 electron, iron 8, 16, plus 3 from the allyl 19. Overall, this being a positive charge. So, this is a 18 valence electron complex. So, the reactivity of this complex stems from the reaction of this eta 3 allyl by triphenyl phosphine resulting in the attack of the phosphine moiety onto this olefin with the formation of this olefinic compound and iron tetracarbonyl phosphine, the way it is shown over here. So, this reaction is not only limited to triphenyl phosphine, but is generic to a variety of nucleophiles, and as a result a large number of compounds can be obtained through this method. So, reacts with variety of nucleophiles to generate intermediate olefin complexes which upon decomposition leads to respective alkenes. So, this is a interesting example whereby eta 3 bound transition metal compound is formed by electrophilic addition to a diolefinic complex, and subsequently the reaction of this eta 3 bound iron compound to various nucleophiles like the phosphine occur at this eta 3 bound allyl ligand, resulting in the formation of the olefins. So, we would now look at a different reaction in which instead of the nucleophiles attacking eta 3 bound allyl transition metal allyl complex, we are going to look at electrophile attacking similar eta 3 bound transition metal allyl complex. Now, here there is a certain catch in terms of the complex, even though these are transition metal allyl complex, in which in the previous example nucleophile attack was considered, whereas the example which I am going to talk about is also an eta 3 bound transition metal compound, but here an electrophile attack would occur. So I must note that in the beginning that these eta 3 bound transition metal compound, however, are different in these two cases. For example, in the former, where a nucleophilic attack happened on the eta 3 bound transition metal compound, it was cationic in nature, and in the present case, where a electrophilic attack would occur onto another transition metal eta 3 bound allyl complex, this complex would be as expected anionic in nature to facilitate the electrophilic attack. So let us take a look at the specific example that involves electrophilic attack at central metal atom and is again governed by the formation of eta 3 bound transition metal allyl complex, as is shown here from FeCO5 plus allyl iodide in presence of sodium amalgam, giving this eta 3 allyl iron tricarbonyl anion, which can then reacts with isopropyl bromide in THF at 0 degree centigrade, resulting in this eta 3 bound iron isopropyl moiety and CO3. So to note over here, the electrophile is this isopropyl cation that is attacking on this eta 3 bound allyl iron tricarbonyl anion. Then subsequently, in presence of light and in acetonitrile at 0 degree centigrade, CO insertion occur along with the formation of this ketone. This is an interesting alpha beta unsaturated compound and is a useful precursor for many synthons in organic synthesis. So the take home message is the electrophilic attack at central atom followed by CO insertion and release of ketone. So what we see that in this particular reactivity, that one can generate ketone by CO migratory insertion, and that in the preceding step one can undergo a electrophilic attack onto a eta 3 bound transition metal allyl anion, and which subsequently can also be generated by the reaction of iron pentacarbonyl with allyl iodide. So let us take a look at this allyl radical and C4H4, particularly with respect to their molecular orbital, as that will explain some of the reactivity issues that we are discussing. So molecular orbitals of C3H3 dot and C4H4. So one can see for C3H3 dot there will be 3 pi type orbitals, and there will be 3 MOs resulting from 3 AOs, which are psi 1, psi 2 and psi 3. In our earlier discussion, we have discussed in details the various molecular orbital combinations that are formed for this allyl radical. Now, allyl's radical has 3 electrons, so psi 1 is paired and populated, psi 2 is unpaired single electron, so it has a radical nature, and this is the highest occupied molecular orbital or HOMO. Thus, the reactivity of C3H3 dot radical is very much dependent on this unpaired electron available at the psi 2 orbital. Now, the psi 2 molecular orbital would resemble or would look like this. Now, in the same context, let us look at how the molecular orbital of C4H4 would be like. So, C4H4 would also have 4 pi orbitals, and then it would have 4 MOs, which will go from psi 1 to psi 4. And each of these would have 2 electrons. So, in this case, the highest occupied molecular orbital is paired up, and it is occupied by 2 electrons of opposite spin. Now, if we look at the molecular orbital diagram of psi 2 of the HOMO, that would resemble something like this. So, these 2 molecular orbital clearly depicts the reason for extremely high reactivity of allyl or enyl kind of ligands, because these ligands, allyl or enyl kind of ligands, have odd numbered of carbon atoms, and these are unsaturated compounds, and also because of the fact that in the neutral form their HOMO just contains one single electron, which makes these ligands very reactive in their neutral form, particularly owing to their radical nature, and hence this further highlights the importance or challenges that are associated with their stabilization as well as their isolation, and also sort of highlights the importance of their stability being achieved through complexation with transition metals, leading to their isolation. So with that, I would finish off this discussion on transition metal allyl complexes, and then move on to another very interesting topic, which are the sandwich complexes. As the name suggests, that these sandwich complexes are complexes of cyclopentadienyl or other ligands of transition metals, cyclic ligands of transition metals, and these are mainly homoleptic or heteroleptic complexes of transition metals, and transition metal is bound to the Cp or the other cyclopentadienyl or cyclohexadienyl octatrianenyl rings through pi electron. Now, I must say that the curiosity on these kind of complexes, sandwich complexes, sort of originates from that of the studies with respect to ferrocene, where 2 cyclopentadienyl ring was found bound to iron, and it aroused a tremendous interest in 1950s and 60s, particularly from the standpoint of understanding the nature of bonding that exists between transition metal and the cyclopentadienyl ring. Now, one of the unique feature about the cyclopentadienyl interaction with transition metal is the fact that Cp ligand interacts with transition metal through the pi electron cloud, and that what led people to try to rationalize and understand such interaction, because it was mainly thought that these ligands are very different from simple sigma type ligands that people were used to before, and they were not sure as to how p type orbital can engage with transition metal in a sigma type fashion. So, having said that, a lot of research went into studying and understanding sandwich complexes, and what turned out at the end that sandwich complexes are not limited to or restricted to only ferrocenes or metallocenes. Various combinations of homoleptic or heteroleptic transition metal biaryl kind of complexes are known there, having different steric as well as electronic demands. So, to illustrate this example, I am going to present to you various kind of sandwich complexes and their total valence electron count, just to give you a feel for as to what kind of different varieties they exist upon. For example, this Cp titanium cyclooctatetraene. So, this is 5 electron, 4 electron, 8 electron, overall 17 valent electron species. The next comes Cp chromium cycloheptatriene. Now, this is 5 electron, 6 electron, 7 electron, overall 18 electron. The next one is Cp manganese benzene. So, 5 electron, 7 electron, 6 electron, resulting in 8 electron species. Then comes ferrocene, 5 electron, iron, so this is 5, 8 electron, 5 electron, overall 18 electron. We also have this Cp, cobalt, cyclobutadiene. So this is also a 5 electron, 9 electron, 4 electron, overall a 18 valence electron compound. Last one is also a very interesting one, which is Cp, nickel, cyclopropene. So this is 5 electron, 10 electron and 3 electron, overall 18 electron species. So one can see that there is, if the Cp remains the same, there is a steady increase in electron density at the metal, and similarly there is a steady decrease in the electron density of the other cyclic ligand of the sandwich complex. However, such that the overall valence electron of these compounds remains the 18. The fact that these compounds has 18 electrons means that they are kind of stable compounds, and that they are at least electronically saturated, and because of the presence of two planar Cp or other cyclic ligands, the metal is kind of shielded from both ends, and hence that also imparts the stability to these transition metal sandwich complexes. So what comes to the fore is the fact that sandwich complexes are not just the ones which are restricted to the central ferrocene atom, from where the interest sort of arose, but one can see that it expands in both the direction in terms of diversity, not only at the ligand but also at the metal center. So with this I will conclude this particular discussion in this lecture, fourth lecture in particular. We have been looking at two interesting aspects of transition metal compounds, particularly in the reactivity of eta 3 bound transition metal allyl complexes, in which we have seen that these compounds, transition metal allyl compounds, can be reacting with electrophile as well as nucleophile, and as a result they can be used to produce olefins or ketones because of their reactivity. We have also looked into the property of their neutral compound being extremely reactive as compared to the C4H4 or the even number carbon containing unsaturated compound. The reason being the allyl or enyl moiety containing unsaturated odd number of carbon atoms are radical in nature with their HOMO containing an unpaired electron, which results in their tremendous reactivity. In the next, the second half of our discussion, we have initiated a new topic, which are sandwich complexes, and in that particular aspect, what we saw that those sandwich complexes has its genesis from ferrocene or bis-cyclopentadienyl Cp complexes, but it sort of diversified into various kinds of combinations of various Cps and other type of cyclic ligands, and also it has huge amount of versatility or diversity arising from the various kinds of transition metal that can form the sandwich complex. So with this, I would like to conclude today's lecture, and we are going to take up the sandwich complex in much more detail in the next lecture, looking into various forms of sandwich complexes are there, what are their diversity, what are their classifications, how they are prepared, and what are the interesting aspects or characteristics associated with the sandwich compounds. So with that, I once again thank you for being with me and patiently listening to this lecture on advanced transition metal organometallic chemistry, and also look forward to being with you in the next lecture, which will talk in more details about sandwich complexes. Thank you.